decent long weekend. The weather has kind of got the best of us today. I'm actually filming on the weekend because there's nothing better to do. I've hit a wall of boredom here, so there's only so much I can really do to pass the time. All right, what we want to get done this week is 5.3 and 5.4. So we're taking it a little bit slower because we have time. Depending on when you're watching this video, they are making an announcement on Tuesday, May 19th, about the rest of the school year. So by the time you watch this, I'm sure the announcements will already be made, so we should have a better idea by then of what's exactly going to happen. Okay, what I want to do with this lesson is a little bit long and drawn out when you actually look at the lesson, which is fine. You'll follow along with it. This first page that I've had is really the highlights. So because I'm not there to explain things to you and get, you guys asking me questions and me being able to answer live, I think maybe a streamlined approach is a little bit better in this scenario. This would not be the way that I teach in a classroom because I don't want to just give you the formula and then say plug the numbers in and solve it. But in a situation like this where I can't really spend the time to answer the questions that you have, this might be the best way that we learn this right now. So the idea here is the last lesson was on the binomial theorem. So the binomial theorem was a way that we expanded binomials. So a binomial to any degree, so it could go anywhere from degree 2, degree 3, degree 4, degree 5. We could expand using a very simple algorithm. Okay, we took n, we chose some value depending on what it was, and then we put our a value to an exponent, our b value to exponent, and we continued doing that and adding them all up. Well, this binomial distribution is something that was derived from the binomial theorem. And if you look through the note, I show you the basic general derivation of where it came from. So it's there for you to look at if you're curious or you want to understand. But I think for the majority of us, and there's still 50 people registered in this course this semester, that maybe the approach that we go right to the formula and go on from there is going to be the best thing. So your first question should be sort of asking me more about what's going on with distributions. So we spent an entire unit looking at the normal distribution. The normal distribution is by far the most widely used statistical distribution in the world. Okay? Any amateur statistician is using the normal distribution all over the place. And that's why it's so widely used in education, because most professors are not statisticians. So they're using not only a distribution that makes most sense, but one that's easy to work with, and that's the normal distribution. That is the one distribution that you're going to need to know the most about moving forward in your math careers. Depending on what you take in university, you will have to there's almost a guarantee that you're going to have to take a stats course, and you'll need to know the normal distribution. From there, there's dozens of other distributions that are used in different scenarios, and we're going to look at 3 or 4 of them in this unit, just to give you a different kind of taste in the direction that your stats career may go if you continue to take stats courses in university. So the first one is called the binomial distribution. And this is only a distribution where you have 2 possible outcomes. One we call a success and one we call a failure. Now we're going to label our success always with a probability P. Okay? And again, probabilities are in percentages, which we convert to decimals almost always. Now, if the opposite of success is going to be a failure, we're going to give that a Q. Okay, so P and Q are our 2 probabilities. Okay, because there are only 2 options, P and Q have to add to 100% or to 1. Okay, so if the options are it's going to rain or not rain, it's currently raining right now. You can probably hear it on my metal roof. And if I say there's an 80% chance it rains today, then that's considered my success. My failure is considered not raining, and it would have to be 20%. They have to add up to 100%. Okay? So that's the scenario we're going to look at. And these experiments that we do have to be exactly identical, and they have to be independent. That means that one doesn't have an effect on the other. Okay? So in the situation with rain, we would say, well, the fact that it's raining today shouldn't have an effect on whether it's going to rain tomorrow. So you can't say, well, it rained yesterday, it's not going to rain tomorrow. Well, it very well could. You know what I mean? So in the experiments that we're doing, we're considering each event to be independent, like flipping a coin. You flip a coin and it's heads, does that mean you have a better chance of tails the next time? Of course not. people that go to the casino and play roulette and say, well, it was red 4 times in a row. It's got to be black this time. No, it doesn't. The same number of red and black on the circle that you're spinning. There's also a couple greens. Okay, so in a binomial distribution, things you need to know. Identical experiments, like same flipping coin, same flipping coin, same flipping coin. Independent, one does not affect a future one. And only 2 outcomes, success versus failure. Now, this is the formula we are going to implement. Again, it comes from the idea from the binomial theorem. In the binomial theorem, if we did an expansion to the power of 4, say, we would start our theorem saying 4 choose 0. A to the 4, B to the 0. Plus 4 choose 1. A to the 3, B to the 1. So on and so forth. This is an exact replica of that idea, and that's why it holds the name binomial, because it came from that binomial theorem. Okay? However, in this case, the variables have changed slightly. There's no longer an A and a B, but a P and a Q. Again, representing our success being P, our failure being a Q. And now we have this new variable K. This definition over here is saying the probability that some random variable X equals K. So K is representative of your number of successes. So say you're looking at a 7-day period and trying to figure out the probability that it's going to rain exactly 3 of those days. You'd say the probability that X equals 3. The probability that the number of successes I have is exactly 3. Number of trials, 7 days. Number of successes we want, exactly 3. Chance of rain, whatever the probability is of rain, is P to the 3. Chance of no rain being Q to the n minus 3, which in this case is 7 minus 3, which is 4. Plug it into the formula, you do one quick calculation, and you're good to go. Throwing my calculator across the room. Okay, so this, if you have to screenshot this, write it out for yourself, this is a very good page to have before you do the assignment, because this is going to give you all the information you need to know for this specific distribution. Okay, again, N stands for the number of trials you were doing. K stands for the number of successes you want. P is the probability of that success. Q is the probability of failure. It's a matter of plugging numbers in and calculating on a calculator. There's no thinking in this. If you can use your calculator, you can solve binomial distribution problems. Okay, with all the distributions we are going to look at, not only do they have a probability formula, they also have an expected value formula. So expected value, we learned in the last unit. I didn't assess you on it because it really comes into play in Unit 5, and so I saved it for Unit 5. In Unit 4, we looked at it as this: the sum of all the x's multiplied by their probabilities. Again, in the note, you can look at it, and I've explained how we derive this and get to this formula. What you need to know at this stage is that this is the formula for binomial distributions. Hold on, I gotta let a kid in. You coming in? Okay, come in. I'm teaching, so. Okay, watch out. I'm teaching, so you gotta be quiet, okay? Okay, so in our case for the binomial distribution, the expected value has to be the number of trials you have simply multiplied by the probability. Okay, that will give us an expected value. Okay, the very last thing I want to talk about before I do a couple examples is if they ask you to find the whole probability distribution. An entire probability distribution is looking at all the possible numbers of successes you can have. Hold on, Morgan. So that means if you're talking about the probability that it rains in a week, you would have to look at the probability it rains 0 days, or 1 day, or 2 days, or 3 days, or 4 days, or 5 days, or 6 days, or 7 days. You have to look at all the possibilities. So if you're asked to find the probability distribution, which you will be in the homework at some point, you have to find all cases. You're much happier when they ask you for a specific probability, like the probability it rains exactly 3 days. Morgan, what do you want to say? You want to come say hi?
Bubba texting me.
Oh, Bubba's texting me?
Yeah.
Okay, well, I'll check when I'm done. You want to say hi or no? You gotta come over this way a little bit. You still in your jammies?
Yeah, I do. In my jammies.
This is true quarantine life. Still in her pajamas. It's actually 2 o'clock in the afternoon on Monday, so.
Wait, it's 2 o'clock. I thought it's 12 o'clock.
No, you had lunch already. Okay, what I want to do is kind of skip ahead, and I'm going to start with example 3. The other examples are there kind of deriving all of this, but I'm considering this sort of the main point here.
Mama, can I answer her?
No, because I'm filming, so just wait. I'm going to be done in no time more.
Like how long? Now?
Give
You're
me 10
erasing everything?
Give me 10 minutes.
Okay.
Okay. So the first example I want to do is example 3. That's in your note. And it says, a pair of dice is rolled 8 times. Find the probability of rolling double 6s. Okay? Dice rolled 8 times. Find the probability of rolling double
Mama,
6s.
what are you gonna do? He texted me.
Just wait, Morgan. Okay, so anytime we roll 2 dice, we almost always need sort of a sum chart to kind of look at it. So in a sum chart, just to refresh your memory, because you'll have to use this again.
Chart?
It's right here. Morgan, I need you to be quiet, please.
Okay.
If you want to stay here, you have to be quiet.
That looks
Okay, so here you're a sum chart saying this is dice number 1, this is dice number 2. Morgan, this is actually something you can handle. So if you roll a 1 and a 1, what does it add up to?
2.
2. If you roll a 1 and a 2, what does that add up to? 3. And that's how this chart works. It tells you just what the sum is as you go across. Okay, and this is something you should be familiar with
I am.
because we've used it quite a few times.
I'm familiar.
You're familiar?
I don't think I am.
But you're good at adding dice.
Yes, I am.
Okay, so they want to specifically look at our probability here that we're going to roll double 6s. Now, in order to do this, you're always going to have to write these 4 things if you know it is a binomial distribution, which is our only option right now because we haven't learned the other ones yet. So n is the number of trials. Well, we're rolling this dice 8 times, so our number of trials is 8. K is the number of successes we want. We just want to roll double 6s once.
12.
Okay, so in our case, K is 1.
12.
P, Morgan, be quiet. P is talking about the probability of rolling double 6s. Well, double 6s only occurs right here. What'd they add up to, Morgan?
12.
12, right? So this is only 1 out of how many options when you roll 2 dice? 1 out of 36. So we only have a 1 in 36 chance of getting double 6s. We have a 35 out of 36 chance of getting anything else. Because remember, these have to add to 100%. Okay?
I need a bubble.
So now, in order to find our probability, we say the probability that x equals exactly 1, we want to get 1 double 6, is equivalent to, now this is the form, I'm just going to write it down first, n choose k, p to the k, q to the n minus k. So we will sub in. Of our 8 rolls, we want 1 of them to be double 6s. The probability is 1 over 36. We only want to get 1 of them. And at the probability of 35 out of 36, that's anything else, we need to get 7 of those out of our 8 rolls. So this is just a matter of plugging this into your calculator. So you'll do the combination first, 8 choose 1, you'll get 8. Then you multiply by 1 over 36 to the power of 1, multiply by 35 over 36 to the power of 7. And in the end, you will get 0.182 far. So they're saying there's an 18% chance that if you roll the dice 8 times, you will get exactly 1 double 6. Okay, so not bad actually. Now, that was part A of the question. Part B of the question says, find the probability you get it at least once. At least once means you get it once, or twice,
Mama,
or 3 times,
Can
or
I ask
4,
you
or all the way up to 8 times.
can I ask
So,
you a
Morgan, be
question?
quiet. So you can get 1, 2, 3, 4, 5, 6, 7, 8. You would have to do 8 calculations to do it the direct method. Or you have to go back, wait, Morgan, to the indirect method, which you will remember
How long?
is 100% minus the opposite. Okay, or the total number of ways minus the opposite. Well, the opposite in this
What's the
case
question
is
for the math thing?
no double 6s.
Okay, yeah, that's good. Mama,
Okay, the opposite of at least 1 double 6 is no double 6s. So when you look at this, the probability of no double 6s, you use this formula again, but instead you use 8, and this time you're choosing to get no double 6s. Be quiet, Morgan. The probability of success is still the same. The probability of failure is still the same. You just change that.
6s.
and you get a 20.2% chance of getting at least one. Yes.
So when we're done this, can we play snakes and ladders to see if we get a double six?
Sure, we can play snakes and ladders to see if we get a double six. Okay, so you just got to be careful. The language around it is going to be similar. So when we did combinations, we talked about a lot of the indirect method and at least and at most. And so you still have to be aware that that's a very possible outcome of what's going to happen. And that you always have the choice. You can do this calculation 8 times. We did it for 1. You can do it for 2, for 3, for 4, for 5, for 6, for 7, for 8. It's just going to take you forever. When the indirect method lets you do it in much less steps. Okay, so use the indirect method when you can. If they're only asking you for a specific single thing in the probability distribution, then you just use the direct method. Okay, if you continue on with the note, example 4 is what I want to do next.
When you're going to be done?
I have 5 examples, Martin.
So you're on the 4th one.
I'm on example 4.
Okay.
Okay, so example 4 says 10 multiple choice questions. 10 multiple choice questions with 5 answers each. So that means they have A, B, C, D, E. What's the probability of getting 6 out of 10? Find the probability that x equals 6. That's really what we're looking to get. We're saying, what is the probability we get exactly 6 out of 10 correct? So again, every time you're doing a binomial distribution question, you're going to select these 4 things. What is the number of trials we're doing? Well, there are 10 questions. How many of those 10 do you want to get right? What is the number of successes you want? Exactly 6. What is the probability of success? So in this sort of question, when you're talking about probability of success, you're really asking if you guessed on a multiple choice question with 5 answers, which was right. You have no idea, so you have no prior knowledge, A, B, C, D, or E. If you got to guess, what was your chance of getting it right? Well, 1 out of 5. Only 1 out of 5 is correct. You have a 20% chance of guessing right. So you can write this as 1/5. If you want to write it as 0.2, that's fine. It doesn't matter if you leave it in fraction or decimal form. That's completely up to you. But what that tells us is if there's a 1 in 5 chance of getting it right, then there's a 4 in 5 chance of getting it wrong. Okay, which is 80%. And remember, what do these always add to? 100%. It has to be success or failure. There's no other option. So once you have all these in, it's easy to set up the question. The probability you get exactly 6 right is equivalent to, and I'll write the formula just to keep it fresh in our minds, but obviously when you're learning online, the formula is always in front of you. You don't have to memorize it. So of the 10 options, choose 6 of them. Probability of success is 1/5 to the power of 6. We want to get 6 of them right, and we only have a 1 in 5 chance. Of the ones we're willing to get, oops, not 5 out of 6, goodness. Okay, your chances of getting it wrong is 4 out of 5, and if you're getting 6 right, how many are you getting wrong? 4 of them. When you actually do this calculation on your calculator, you get 0.0018.
0.008?
That's not even
That's
1% chance. 0.18% chance of getting exactly 6 out of 10 right if you're guessing. That means you have no prior knowledge. If you just went into a multiple choice question of, say, like a 3rd or 4th year university math course, and there was 10 multiple choice questions, if you thought you could get at least 6 out of 10, your chance of getting exactly 6 out of 10, I should say, is less than 1%. Very, very small. Your chances of getting perfect, if you look at the calculation we did here, your chance of getting perfect, so in this case we change this to x equals 10, is 0.00060102. Almost impossible. Your chance of getting 0 correct, however, the chance of getting 0 out of 10, because you have 4 out of 5 options are wrong, you actually have a way better chance of getting a question wrong than right. You actually have almost 11% chance of getting all the questions wrong. So guessing is never sort of a good idea.
Mama.
Okay. Yes, Morgan.
Are you on the 5th one?
I'm on the 5th one now.
Yay.
Okay, the last one kind of wants to look at our idea of expected value. So once we get through that one, again, you've probably noticed on the on the quizzes and on the test, we try to give questions that are fairly straightforward based on the
It
lessons.
stopped raining.
Good. Okay, so example 5 says a game consists of cutting a deck of cards 5 times. So you're cutting it 5 times. That means the number of trials you have is 5. If you get a face card, you win $2. Face card equals win $2. Trying to figure out what all this is. It costs $5 to play
Costs $5 to play what?
this game.
What game?
So you got a deck of cards.
I wouldn't do it.
You got to flip a card. If you get one with a face, which is a jack, queen, or king, you win $2. But it costs you $5 to play. Okay, is this a fair game?
I don't think it's fair.
Okay, so basically what you have to look at here, what could happen essentially is that
But isn't a face a joker?
no, a joker's not a face. There's no jokers in the deck. You're flipping it 5 times, right? So you could get 5 face cards, in which case you'd win $10, but you only paid $5 to play. So you're kind of looking at what are your odds of getting a face card in the first place. So to use the expected value formula, it's n times p, the number of trials you have, which we know is 5, multiplied by the probability of success. So in this case, we do not have a probability of success. You don't think it's a good idea? You think you're going to lose?
Yeah.
Okay, well, let's see what happens.
Pick up that.
Probability of success is exactly how many face cards are in a deck out of the total number. So there's the jack, the queen, and the king. 3 different face cards. There's 4 different suits. So there's 12 face cards out of 52. Just wait, Morgan. So these are the 2 values we need to know to find the expected winnings that you're going to get. So 5 times 12 out of 52. You multiply them, and you're expecting to get 1.15 face cards. Basically, that's what's saying. The expected number of face cards you're going to get when you play this game is 1.15. Well, every face card you get comes with a winnings of $2. So if we multiply that together, when you play this game, you're expected to win $2.30. But how much did you pay to play? $5. So how much did you actually lose? Yeah, you win $2.30. Yeah, you lose $2.70. You're right, Morgan. Almost $3. Okay, you actually lose money in this game. So is it a fair game? No, not at all.
No.
It's only considered fair if your expected payout is the same as what you paid to play.
Mom, I want to ask you a question.
Okay, yes.
When we're done playing that game, and we played that game, but with no money actually.
This game?
Like
Just to see?
Pick up card and
Yeah, maybe when we go inside.
see.
Okay, so that's the idea with expected value. So you should be able to get started on the binomial distribution homework. Follow just the basic binomial distribution formula. Follow the expected value.
That actually good.
Throw. There we go. Putty. That's disgusting, Lauren.
Hey,
it's on the
give
top
it back to me. You can stick
Okay.
on the floor.
Thank you. Next up, geometric distribution, I believe.